Okay, so this is lecture 9. We're going to do equivalence relations and equivalence classes. Pretty much carrying on from last time. There's still a few spare handouts at the front, but most of you should already have them. So we looked at a lot of examples of relations last time on various sets, and we're going to look at some more this time. Here's one we discussed last time, congruence modulo 2. That's x is related to y, if and only if x minus y is even, which we could also say as if and only if 2 goes into x minus y exactly. So it's x minus y is divisible by 2. That's one of the easiest ways of working with it, as we'll see in a minute. Now, here are some properties that this has, and I'll just show you, I'll prove that these properties for you as well. And they've got names, right? Now, these following three conditions hold for all x, y, and z in S. Well, S is just the integers at the moment, okay? S is going to be our current set, which is z at the moment, so that's the integers. And for all integers, x, y, and z, perhaps you normally use m, n, k for integers, it doesn't matter. For all integers, x, y, and z, x is related to x. The fact that that's true for all x is described by saying R is reflexive, which means something to do with yourself, right? So x is always related to x. So for all x in the integers, we have x minus x equals 0, so 2 does divide into x minus x. I'll remind you that 0 is even in this module. 0 is divisible by 2, because 0 divided by 2 is an integer. We can't do 2 divided by 0, but we can do 0 divided by 2. The next one. This is for all integers x and y. It's true that if x is related to y, then y is related to x. Why is that? Well, if x minus y over 2 is an integer, then y minus x over 2 is equal to minus x minus y over 2 is also an integer. So whatever pair x and y you take of integers, if x minus y is divisible by 2, then y minus x is going to be divisible by 2 as well. So you've got symmetry. And the fact that this works for all integers x and y, of course, it's an if statement being true for all x and y. For those x and y where x isn't related to y, this is true automatically. Because whenever you say if something that's false, then that one's true automatically. But so the only interesting ones is the ones where it is true that x is related to y, and then it has to be true that y is related to x. And finally, this last one here, this is the transitivity one. Again, it has to be true for all x, y, and z. So you check for all x, y, and z, but the only ones you're interested in checking are the ones where x is related to y and y is related to z. Because as usual, there's nothing to check if one of these is false. If the left-hand side is false, then the if-then statement is automatically sort of vacuously true. Okay? So when you're checking an if statement, you only have to check the cases where the thing that you're saying if is actually true. And then you have to check that the other thing is true in those cases. So let's have a look at the transitivity. So let x, y, and z be integers. Remember, S is Z at the moment. Suppose that X is related to Y and Y is related to Z. We have to prove that X is related to Z. That's our target. As usual, we haven't proved it yet, so this is our target. Not yet proved, but worth remembering where you're going. Okay, we haven't proved it, so we mustn't make deductions from it. Okay? Never make deductions from your target. It's just, I'm putting that in there to remind us where we go. Okay? So we don't yet know that X is related to Z, but we do know X is related to Y and that Y is related to Z. That means, thus, X minus Y over 2 is an integer, and Y minus Z over 2 is an integer. Remember, that's just saying that X minus Y is even. That's X minus Y is even, or X minus Y is divisible by 2. And this is Y minus Z is divisible by 2. Okay? And then, let me just check that that's the way around we said it. Yeah, that's the way around we said it. Okay, so now we have to look at X minus Z over 2. But you can see that's equal to X minus Y over 2 plus Y minus Z over 2. So that's a sum of two integers, so it's an integer. And so 2 divides X minus Z. As required. Okay. By saying let X, Y, Z in the integers, that means we're trying to prove something for all triples of integers. Whenever you want to prove something true for all triples of integers, you're going to start with let X, Y, and Z be an integer. Be integers. Then we take the assumptions we're supposed to make, that X is related to Y and Y is related to Z, and then we have to prove that it follows that X is related to Z. And that's what we've done here. This 2 divides X minus Z is the one that says X is related to Z. Alternative approaches, by this stage, I think I'd allow you to quote that a sum of two even numbers is even. Okay? So another way of thinking about this is we're proving that a sum of two even numbers is even. So that's another approach. A sum of two multiples of 2 is another multiple of 2. Lots of different ways of going about this. This is just one of the ways of doing it. Any questions about that one? Okay, so that's a pretty easy example, but an important one. We're going to do the same again for congruence modulo other integers rather than just 2. This is an example of something called an equivalence relation. An equivalence relation is a relation that satisfies those three conditions we just had. So the thing has to be reflexive, symmetric, and transitive. The reflexive one says that for all x, x is related to x. So this has to be, so this is reflexivity. So this is reflexive, means this holds for all x, not just some. So you don't start looking to see, are there any x's that are related to themselves? To get reflexivity, every x has to be related to itself. Every x in the set. Again, for this one here, this is symmetry, or symmetric. This holds for all x and y. I'm not saying that all x and y are related. I'm saying that whichever x and y you take, if x is related to y, then y is related to x. notice, oh, look at this, we use a different symbol. I've told you could use almost any symbol, and this is one of the common ones, this wriggly line symbol, which people pronounce in lots of different ways, as wriggles or twiddles, or everybody pronounces this differently. It's a sort of similar, no, it's also sometimes called similar. But anyway, it's a typical notation for a relation that might be an equivalence relation, and it's very often used when you do get an equivalence relation. Right, so this is symmetric. Again, must hold for it to be symmetric, it must hold for all x and y. And this last one, that if x is related to y and y is related to z, then x must be related to z. Again, this is whichever triple you take, if you find the first two work, the last one has to work as well. So again, you have to check this for all x, y, and z, which is what we just did for congruence modulo 2. So this is transitive. It must hold for all x, y, z in S. X, y, z in S. I don't think I've done very much with these quantifiers, so I'm just going to have a quick aside on quantifiers here. So let me just have an extra page. I want an extra page. Thank you. So an aside on for all of there exist. So for all x, y, z in S can be abbreviated this is pronounced for all x, y, and z in S. Okay, so that upside down A is a for all. It's on your notation sheet. If you haven't got, it's the first notation sheet I handed out. If you haven't got that, you might want to print it out from the Moodle page, or get a spare copy from me sometime. There's a notation sheet here, but this is the second notation sheet I've handed out. So if you haven't got the first notation sheet, that's got these things like this for all on it. So E1 really, if you put the quantifier in, you can interpret this as saying for all x in S, we have x is related to x. That's reflexivity. So you could write that out as all x in S, comma, x is related to x. That's pronounced the same way. That's just a shorter way of writing in mathematical symbols. For all x in S, we have x is related to x. Okay? So that's pronounced the same way. And suppose you want to negate that. The negation, not reflexive, is there exists x in S such that x is not related to x, which is short for what I just said. There exists an x in S such that x is not related to x. Put a line through the relation symbol. So that's quite a short way of writing it. And it's quite good. When you're doing negations, the for all will turn into whether exists, and anything that was true becomes false. Well, you've had a bit of practice at negating things by now. You have to do it in ACF. You need to be able to negate in this module as well, because often the easiest way to prove a statement is to prove it's contrapositive. But sometimes the contrapositive is, for some reason, sometimes the contrapositive is easier to prove. But if you want to prove the contrapositive, you have to be able to write down the correct contrapositive, which usually involves negating something, and the statements you're negating have normally got some for alls in, which have to turn into there exists, and then sometimes there are some exists which have to turn into for alls, and you have to make sure that you negate the conclusion as well. So a bit of practice in negating is a good idea. Right, let's get back to first question. Okay, so go back and have a look about what we meant was by reflexive, symmetric, and transitive. And you have to think about the less than or equal relation on R and try to decide how many of these are true. Is less than or equal reflexive? Is less than or equal symmetric? Is less than or equal transitive? So I'll give you a couple of minutes to think about that, and then we'll get some votes. And I'll pause the recording, and then we'll see what you come up with. Another 10-second wait. Okay, let's see what people have voted for. There you go, 73 answers. So if you could have some quiet, please. If you could have quiet, please, let's see what we've got. We've got 73 answers. Let's see if there's any more. Up to 79. A big majority going for C, and not much else, a little bit, a few people unclear about what it means. Let's see if I can explain, by giving you the answers, explain what's going on here. Okay, so looks like most of you are pretty clear about this, or at least you've got the correct number of answers, because that's correct. So let's see which ones are right and which ones are wrong. Is the relation less than or equal to reflexive? So this is the question. So in other words, that one's saying for all real numbers R, we're supposed to have x is less than or equal to x. And this is true. Real numbers are less than or equal to themselves, because remember, it's less than or equals. So since equals holds, we're OK. The transitive one, this is saying if x, y, z are in R with x less than or equal to y and y less than or equal to z, then x less than or equal to z. And this is true. It's a standard thing you've learned in ACF about the way inequalities hold. But you can think about where they are on the number line. X less than or equal to y says that x is to the left or at the same place on the number line as y, and y less than or equal to z says that z is to the right or in the same place as y on the number line. So although I'm not saying this is a proof, because this is just a standard thing about inequalities. But typically, in general position, they're going to look like something like this, except that x might be equal to y, and y might be equal to z. But you've got x less than or equal to y means that x can't be to the right of y, and z, and y is less equal to z means z can't be to the left of y. So therefore, x can't be to the right of z, because y is in between. Okay? That's not a proof. It's just a visual representation of something you already know from ACF. So this one is true. So we'll say this is a standard from ACF. Okay? And the middle one is the one that fails. It's not symmetric. And this is the one that can cause a bit of confusion because you need to give an example. So that means I need to find an x and y where x is less than or equal to y, but y is not less than or equal to x. And so I use my favourite example. We need a counterexample. For example, 1 is less than or equal to 2, but 2 is not less than or equal to 1. Okay? I put a line through the less than or equal. Of course, the line through less than or equal means greater than when you're dealing with real numbers. So 2 is greater than 1. 1 is less than or equal to 2 because it's less than or equal, and in this case, less than holds. Okay. And when you want a counterexample, remember a counterexample to symmetry, not symmetric, means you have to negate symmetric. Negate symmetric. Let's see, you've got any space down here? Just make a bit more space for this one. We have to negate for all x, y in R, for all x, y in R, if x less than or equal to y, then y less than or equal to x, means that's a tricky one to negate. That's there exists an xy in R such that it's not true that if x less than or equal to y, then y is less than or equal to x. That's a tricky one to negate. So you're going to have to think about that one. You have to get there exists an xy in R such that x is less than or equal to y, but y is not less than or equal to x. Now, I'm trying to figure out the mechanical way of negating that. It would probably be better to... this is what you get if you think about it. There's probably a more mechanical way of doing it, and I'll have to think about that again as to the best way. X less than or equal to y implies y less than or equal to x. So what you're trying to do is show that x less than or equal to y does not imply y less than or equal to x. X less than or equal to y does not imply y less than or equal to x. It's the same as saying you can find one where x is less than or equal to y, but y is not less than or equal to x. And in this case, we've got the counterexample where x and y, you can prove an exist statement with one counterexample. You can prove there exists x, y. You can prove that statement with one pair x and y. That's why you can prove this one true with one x, y. That proves the other one false. You think of it as a counterexample to the other one, and it's an example demonstrating this one. And the example we've gone for is x equals 1, y equals 2. That demonstrates that reflexivity fails. I'll see if I can think of a more mechanical way of negating that statement, because that's otherwise a bit tricky. Okay. Right, so let's have a look at some more examples and non-examples. So here are some standard ones on R. Less than, less than or equal, not equal, greater than. None of these are equivalence relations. Not equal is symmetric but doesn't satisfy the other ones. Less than or equal, less than, greater are not symmetric, but they are transitive, because that's the way order works. So the order relations, so less than or equal, greater than, these are standard sort of what you call order relations, and they're always transitive. The less than or equal and the greater or equal are reflexive, but less than and greater than are not only not reflexive, they're actually called irreflexive, which they've got this special property that, well, okay, for example, you've got, if x is less equal to y and y is less equal to x, it forces them to be equal, which is, so that's a special, that's an even more powerful thing that order relations satisfy. And other kinds of relations, even if they are transitive, it doesn't mean to say that if you know them both ways round, they're going to be equal. And let me not go into that in any more detail. Let's just say these ones you can check that not equal is only symmetric and it doesn't satisfy the other two, whereas these other ones, the order relations, were transitive, and they're reflexive if it's less than or equal or greater or equal, but they're not reflexive if it's strictly less than or strictly greater than. I'll leave you to think about those. You can use equality, and indeed you can use not equality on any set. The equality relation, equals, on a set is always an equivalence relation, and it's very boring, and so is the trivial relation, that's boring as well. So equality, remember, so it's completely trivial if you start writing down what's going on with equality. In fact, it looks really silly. So the proof for equals looks silly. X equals x, and if x equals y, then y equals x. And if x equals y and y equals z, then x equals z. And I don't think I can say much more than that. That's why equals, whatever set you're working on, always works as an equivalence relation. The trivial relation, you have to remember what it is. The trivial relation is the one where everything is related to everything else. So the trivial relation is the boring one where all x and y are related to each other, and all y and z are related to each other. And then everything is also completely stupid, because in the trivial relation, x is related to x because everything's related to everything else and themselves. And then when you're trying to check if x is related to y, then y is related to x, you hit the snags that x is always related to y, but it's not a snag because y is always related to x. So that one's true. And then you have to check transitivity, and the issue is x is always related to y and y is always related to z, so you've got to check a lot of x's and z's. But since all the x's and z's are related to each other, you're okay again. So the fact that the trivial relation, where everything's related to everything else, is a very boring one to check the conditions for. The empty relation, though, is the other way around. That's the one where nothing's related to anything else. But a peculiar thing happens. It's still symmetric and transitive, because there's no counterexamples. When you've got the empty relation, so the empty relation R, we have x is not related to y. That's supposed to be R of a line through it. I'll just try that again. X is not related to y for all x and y. Now remember, not reflexive I wanted not symmetric. Not symmetric would need, there exists x, y in S with x related to y, but y not related to x. But you can't do it, because there aren't any x with x related to y, so there's none of these examples, so there's no counterexamples to reflexivity. That's another one of these things where something is vacuously true. It's another one of these irritating things about the empty set. So the empty relation is symmetric, and for the same reason it's transitive. You can't find any counterexamples, because to get a counterexample to transitivity, you have to find x, y, and z with x related to y, y related to z, but x not related to z. The x not related to z would be fine, but you can't find any x, y, and you can't find any x and y with x not related to y. With x related to y. So there's no counterexamples to transitivity either. So this stupid empty relation is symmetric and transitive, but it's not reflexive unless your S is actually empty, because you do get a counterexample to to reflexivity, because if you've got any x's at all, the empty relation will have x not related to x, and that gives you a counterexample to transitivity, to reflexivity. Right. Okay. Congruence modulo k. Here's one of our most important examples. We did k equals 2 earlier. So here, our relation, so we keep this k fixed, that's our modulus. Earlier we did k equals 2, but k could be some integer now. We'll be particularly interested in things like 9, 10, 11, they're quite nice. But I mean, we have to keep k general at the moment. We say x is congruent to y modulo k. This is for x and y in z. We have x is congruent to y mod k, if and only if k divides into x minus y. Okay? And we did 2 earlier. Now, the same proofs that worked for 2 earlier show that this is an equivalence relation. So this is the relation, right? You can call it R if you like, but normally you would write x is congruent to y modulo k. Okay? That's how you pronounce this one. And this is our relation. So reflexive is because for all x in z, we have x minus x equals 0. So k divides x minus x. Naught is divisible by everything. You can't divide by naught, but naught is divisible by everything. Thus, x is congruent to x mod k, which is our relation at the moment. Now we check symmetry. Suppose x, y, I, and z with x congruent to y mod k, then k divides x minus y, i.e., I'll go back to the other way of doing it. X minus y over k is an integer. But then y minus x over k is equal to minus x minus y over k. It's still an integer. So k divides y minus x as well. And y is congruent to x mod k. So we showed that if whenever x and y are integers with x congruent to y mod k, then y can be congruent to x mod k. And transitivity is like before. To congruence mod 2 above. So given x, y, z integers with x congruent to y mod k and y congruent to z mod k, we had k divide x minus y and k divide y minus z. So k divides, at this time, if you've got two modules, you can add them, and I'll assume this one, x minus y plus y minus z. We've done this before in lectures anyway. If you've got two things divisible by k, then their sum is divisible by k. But x minus y plus y minus z is x minus z. In other words, so x is congruent to z mod k as well. And that proves transitivity. Okay? You take any three integers and you assume that x is congruent to y mod k and that y is congruent to z mod k. Our target is to prove that x is congruent to z mod k, which we've done this way. Okay, now I want to tell you about equivalence classes. And we look at, I'll just remind you what we have with congruence modulo 2. When we had integers m and n, m was related to n by, that was, if and only if m is congruent to m modulo 2, that was when 2 divided m minus n. And that splits z up into two pieces, the odd numbers and the even numbers. All the odd numbers are congruent to each other, modulo 2, and all the even numbers are congruent to each other, modulo 2. If you subtract an even number from an even number, you get an even number. If you subtract an odd number from an odd number, you get an even number. But if you subtract an even number from an odd number, or an odd number from an even number, you get an odd number. So if I write O for the set of odd integers and E for the set of even integers, every integer is in exactly one of those two. And now I can look at those two sets, and I now form a set curly C, which has got those two sets in. This is a set of sets. It's a collection of sets. One of the sets is the set of odd integers. The other is a set of even integers. And you get what's called a partition of Z. I'll tell you more about partitions in a bit. Okay? But O is a set of integers which are congruent to 1. Odd numbers are those integers which are congruent to 1 modulo 2. And the even integers, that's a set of integers which are congruent to 0 modulo 2. And it turns out that every equivalence relation behaves the same way. So if you do congruence modulo 3, you get 3 sets of integers depending on what your remainder is. If you divide an integer by 3, you get remainders 0, 1, or 2, and that tells you which congruence class you're in. So I'm not going to have time to go into more detail of that. Let me say that if you divide by any integer, then the possible remainders are 0, 1, up to k minus 1. So you divide by k, a natural number k. For example, if you divide by 1, the remainder is always 0. You can divide by 1, and the remainder is always 0, but it's not very exciting. If you divide by 2, the possible remainders are 0 or 1. If you divide by 3, the possible remainders are 0, 1, or 2. If you divide by a general positive integer k, the possible remainders are 0, 1, 2, up to k minus 1. That's what happened with our quotient to remainder. It's basically long division and find out what the remainder is. And those remainders are give you the different possible classes you're going to be in. And I'll say more about equivalence classes next time. Now, there's time, I think, for a quick question, but I can only give you about a minute for this, which is, if we're working modulo 9, so I have to see, what's the remainder when you divide by 9? Is it 0, 1, 2, or 3? And how do you work it out? I'll just give you half a minute or a minute to try and figure that out, see if you know any quick shortcuts. There's something called the rule of 9, if you know it, which can give you a shortcut for this. And I'll go into that in more detail. So just, I'll give you half a minute to think about that one and see if you can work out the remainder. Oh, sorry, don't vote yet. I haven't zeroed the answers. Okay, you're free to vote now. Okay, not got many answers yet. So if you're going to vote, please vote soon. "28 answers so far. Okay, I'll now reveal what the correct answer is, which most of you have gone for. That needs a refresh. 36 answers, most people going for B, which is correct. Now it turns out that if you want to work out the remainder modulo 9, the remainder when you divide by 9, all you have to do is add up the digits and then try again. So if you add up the digits of your number, you always get the same remainder modulo 9 as before. Now, when you add up 1 and 2 and 1 and 2 and 1 and 2, that's already 9. That's not going to help you. And then you do another 1 and 2 and 1 and 2 and 1 and 2. So when you add the digits, that's 18 so far. Add the digits, and you get 19. Add digits again, and you get 10. And again, and you get remainder 1. This is the rule of 9. And I'm going to explain later why it works. Okay? And 1 is the correct remainder. We're going to see why that works in a bit. So I think I'll just say a couple of words about this, but then I'm going to have to let you go, and we'll revisit this slide next time. Because we're going to have to do this properly next time. Okay, so whenever you've got an equivalence relation, you get what's called an equivalence class, corresponding to the equivalence relation, for each x, which is which other elements are related to you. And when we dealt with odd and even numbers, those were the equivalence classes working modulo 2. Those things related to 0 gave you the even integers, and those things related to 1 gave you the odd integers. And our notation for this is to put a square bracket around something to say which things are related to you. So the even integers, when you're working with congruence modulo 2, the even integers are those things related to 0. So you put a square bracket around the 0 to mean those things related to 0. And for the odd ones, you do those things related to 1. And when you're doing congruence modulo k, you do the same thing. You say those things that leave the same remainder as you when you divide by k. So this square brackets around 0 means those things that leave remainder 0 when divided by k, which means multiples of k. Whereas the square brackets above 1 means those things which are related to 1, those things which leave the same remainder as 1 when you divide by k, which means those things which have remainder 1 when you divide by k. and you chop the integers up this way. And we'll come back and look at that property next time, and we'll also see why the rule of 9 works, and do similar thing for 11.